we're starting our new unit. We're going to continue to work with trigonometry this unit and next unit as well. So first of all, as we get more into our trig, we need to talk about radians. So that's the focus of our lesson today. Before we get too much into radians, I wanted to remind you about circumference. So the circumference of a circle is the, I don't know, you could call it the perimeter. It's the length of that outside edge of the circle. So if I wanted to find the circumference of the circle, I could use the circumference formula, which tells me that the circumference is equal to 2 pi times the radius. Well, this circle happens to have a radius of 6.5, so it'd be 2 pi times 6.5. And if we wanted to leave that radius in exact length, we would want to not get a decimal approximation, but leave that pi in our answer, and we would say that the circumference is 13 pi. That's 2 times the 6.5, and then we just leave the pi. If we wanted to know in decimal terms how long that circumference is, we could definitely get a decimal approximation for that simply by calculating it in our calculator, and the decimal approximation for this would be 40.84. So the 13 pi would be an exact solution, an exact answer, and this would be an approximation that's been rounded. Okay, you should be familiar with circumference from prior math classes. Well, what if we only had a portion, or only wanted to find the length of a portion of the circumference? For example, what if we had half of the circumference, like this? We wanted to know how long this is. Well, first of all, this is called an arc. Any portion of a circumference, any curved line is called an arc. So this arc, if we want to know its length, we can still think of that circumference formula, C equals 2 pi r, but this time we have to think about what portion of the circle we have. Well, in this case, the portion of the circle we have is half, and the circumference is, again, 2 pi times the radius, 2 pi r. Well, if we calculate that, if we leave it in exact form, we would have 1/2 times 2 times 6.5, which is 6.5 pi. Or if we wanted a decimal approximation, we would just calculate that with our calculator to find that that is about 20.42. Now this is the same radius we were using for our last circle that we found the entire circumference of, and you can see this is just half of that. Well, half is easy to think about, but what if we don't have that nice fraction? What if instead we know the measure of the angle? So this says that I want to know the length of this arc. Here's this little arc. It's a small piece this time. I want to know the length of this arc if it is subtended by an angle that is 35 degrees. Well, 35 degrees is just a portion of that circle, so we can think of this the same way. We'll think about what the portion of the circle is. We have 35 degrees out of, well, an entire circle, if we rotate it all the way around, would be 360 degrees. So we have 35 degrees out of 360. That's the portion of the circumference that we have. And we just multiply that by the circumference. Again, 2 pi r, and our radius is, we're still going to work with 6.5 here. And we just multiply that together. And I'm going to just go ahead and get a decimal here, just an approximation here. So our arc length is about 4, just under 4, 3.97. So when you have these portions of the circumference, they are called arcs. When we're talking about how long they are, we often use that word arc length. Okay, so now I had you work on a couple of practice, so we can do these together. Usually when we talk about arc length, the symbol we use for it is S. So for these, we'll think of the arc length as the portion of the circle that we have. So this one is 100 degrees out of 360 degrees. And we want to times that by the circumference. In this case, that is 2 pi times the radius, which is 5. And let's see. Oops, sorry. My calculator, I hit the wrong button. So the arc length here would be 8.73 units. Again, what we're finding is this length here of this arc. And for this second circle, again, the arc length, we'll think about that portion of the circle. We have 225 degrees out of 360, and we'll times that by the circumference, 2 pi times 17.2. And we find that this arc length has a length of 67.5. And again, we were finding the length of this arc. Okay, now we're ready to talk about radians. Well, in the past, you've always measured angles using the units of degrees. So you measured angles and you knew that, for example, a straight angle or a straight line is 180 degrees. You know that the corner of a square is 90 degrees. Well, degrees aren't the only way to measure angles, and it turns out in math there's actually a unit that at times ends up being a lot easier to work with, and that unit is called a radian. So we need to learn how to measure angles in radians. We're still talking about angles, we're just going to find a different unit for measurement. Sort of like you could measure a length in miles, or you could measure a length in kilometers. You're used to working with degrees, but now we're going to learn how to measure in radians. So a radian is just the amount of rotation needed so that the arc length intercepted is the same length as the radius. And that's kind of a hard definition. So I'm going to use this little applet to show you what that looks like. So I'm going to take that radius that's blue and just wrap it instead around the edge of the circle. Oops, too far. Well, the angle created right here, sorry, this angle is exactly 1 radian. And 1 radian is equal to about a little teeny bit over 57 degrees. So let's see how many radians there are in half a rotation. So let's keep wrapping. That would be a 2 radian rotation. This is a 3 radian rotation. So it looks like if we want to wrap halfway over to here, it's a little more than 3. And in fact, it's exactly pi radians for half a rotation. And if we continue wrapping, we could continue wrapping radians around the edge. And again, the rotation is what we're looking for, this angle near the center of the circle. Right now we're at an angle of 4 radians. This is an angle of 5 radians. Oops, there's 5 radians. And 6 radians almost gets us back to where we started. It's 6.28 radians, or exactly 2 pi radians. So these radians are just another way of measuring an angle, kind of similar to degrees, but different. different measurement. So here's another one, just shows you that 1 radian rotation. If you wrap that radius around the edge, the rotation necessary, so the angle is 1 radian. Okay, like I was saying, half a rotation is exactly pi radians. A full rotation is exactly 2 pi radians. In class, we used a protractor to measure some radians with a radian protractor. Um, if you missed class, you missed out on that fabulous experience. So uh, we're going to start sketching some radian angles in standard position, just like we have been sketching angles in standard position that were measured in degrees. So before we start, I wanted to look at the coordinate system and talk about these angles that are at the axes. So we start in standard position over here on the positive x-axis. So this is 0 degrees. So let's do the degrees first. If we rotate up to here, you all know that that's 90 degrees. If we rotate all the way to the other side of the x-axis, that is 180 degrees. If we rotate it all the way down to the negative y-axis, this would be, sorry, not negative, 270 degrees. And one full rotation, you know, in degrees is 360. Well, let's think about that in radians now. We've just started talking about radians. So let's see. In radians, if we start here at 0 radians, all the way to the other side of the x-axis, a half of a full rotation is exactly pi radians. And if we go all the way around, it's 2 pi radians. So let's figure out these other two angles. So if this is pi, well, this is exactly half of that. We would write it as, usually, pi over 2. It's half of pi. On the other side, well, this is pi. So if we go all the way to here, it's pi plus another half. You could think of it as 1.5 pi, but we don't really like mixed fractions very well in upper math because they can be confusing. It almost looks like 1 times 1/2 pi. So we prefer to write it improperly as 3 pi over 2 as an improper fraction. But improper fractions in higher math are much better. So we've got in radians 0 radians over here. If we keep rotating, 90 degrees is the same as pi over 2, or pi halves radians. Over to here, we get to pi radians, half a rotation. Then comes 3 pi over 2 radians, and then all the way around is 2 pi radians. Let's do it in decimal radians this time. Starting at 0. Well, if I rotate all the way to the other side, I know it's pi radians. That's the same as 3.14 radians. Just another way of writing it. And that's approximately 3.14. All the way around would be 2 pi radians is the decimal. That's about 6.28. Up here, it's half of 3.14. We say that's 1.57 radians. And if we think about this angle down here, 3 pi over 2 is the same as 4.71 radians. Sometimes it's useful to know those decimals because if you're trying to eyeball where 2 radians fits in, it's helpful to know those numbers. But oftentimes, most of the time, we'll think about these angles in terms of pi, like pi, pi halves, 3 pi halves. Okay, so we're going to sketch some angles in radians, just like we did last unit with degrees. We're going to start with an easy one, pi over 2. Well, we know this is pi, so half of pi would be here, pi over 2. Now we're going to get into some fractions that aren't quite as easy. So let me show you how I like to think of it. Here's 0 radians, and we know that half a rotation is pi radians. Well, this particular question is asking us to think in fourths. So if this is 0 over here, and this is pi right here, well, this is 1 pi over here. Well, that's the same as 4 over 4. So that would be 4 pi fourths. Well, halfway between 0 and 4 pi over 4 would be 2 pi over 4. Or if we reduced it, it would be pi halves, but I want to look at it in that non-reduced form for a second. So that means if I'm trying to figure out where 3 pi over 4 fits in, it fits in halfway here. That's 3 pi over 4. Let's try another one. Easy peasy again for a second. Sketch pi radians. Well, we know pi radians is exactly half of a rotation, so there's pi radians. Back to fourths for a second. We're going to think in fourths again. This is 0. This is pi. That's the same as 4 over 4 pi. Well, halfway would be 2 pi over 4. And if half a rotation is 4 pi over 4, we could think of a full rotation as 8 pi over 4. That reduces to 2 pi, which we know is one full rotation. And halfway between the 4 pi over 4 and the 8 pi over 4 would be 6 pi over 4. So we think about where all these different things fit in, and the one that we want to sketch is 7 pi over 4. So that would fit in right here between the 6 and the 8. So there's the angle 7 pi over 4. Let's try it with a different denominator now. We tried a couple of fourths. Let's think in sixths now. 11 pi over 6. Well, we know this is 0 and this is pi. So if we're thinking in sixths, then this would be 6 pi over 6. Well, if this is pi, if I come all the way back over to here, that's double that rotation. So this is 12 pi over 6. Halfway between the 0 and the 6 pi over 6, I got to have 3 pi over 6. And halfway between the 6 and the 12, I've got 9 pi over 6. So where does 11 fit in? Well, 11 would fit in between the 9 and the 12, closer to the 12 for sure though. Ooh, my board's not aligned very well. So there's the angle 11 pi over 6. Okay, last one of these is that we want to sketch 2 radians. Now this is 2 radians, not 2 pi radians. If there's not a pi there, don't put it there. It's just 2. So I'm going to think in decimals for a minute. Here's 0 radians. All the way over here is pi radians. We could write that as 3.14. Halfway in between 0 and 3.14 is 1.57. So if I'm trying to sketch 2 radians, it's in between the 1.57 and the 3.14. At first, it's kind of tricky to sketch these radian measurements. You're all really good at sketching degrees, and you're going to get really good at sketching radians. We'll just practice and you'll get better at it. But it is a little hard at first with those fractions. Okay, so we want to go back and revisit arc length now that we've talked about radians. Well, when we were talking about arc length before, we said it was a portion of the circle times by the circumference. Well, in radians, our portion is out of 2 pi, a full rotation, instead of out of 360. And circumference is 2 pi r. So when you have some angle out of 2 pi and you're timesing it by 2 pi r, the 2 pi's reduce. So the arc length formula in radians is r theta. S is equal to r theta. Well, in this particular case of this circle we have here with this green arc, the arc length is equal to 7 is the radius times 2 is the angle. So the arc length is 14. Now this formula, S equals R theta, it only works if your measurement is in radians. So it's a great formula, very simple and easy formula to use, but it only works in radian angles. Otherwise, you still have to think about that portion of the circle out of 360 for degrees. So let's try a couple of arc length problems in radians. So here is a circle. We have an angle 2 pi over 3 is our angle. Our radius is 5, and we want to know what's the length of this arc. Well, since my angle is measured in radians, I can use the formula r theta. So the arc length is 5 times 2 pi over 3. Well, if I want to keep that exact, I could times that 5 by the 2 pi to get 10 pi over 3. So that would be an exact length of the arc length. If we wanted a decimal approximation for that, we could calculate that in our calculators, and we get, oops, about 10.47. We can also use this formula if we know the arc length and we want to know the angle. So the formula is S equals R theta. In this case, we know the arc length is 17.5 and we know the radius is 7. We're trying to find theta. Well, if we want to solve this formula for theta, we just divide by 7. And we find that 2.5 is equal to theta. That's 2.5 radians. Now, it can be dangerous to assume that your diagram is to scale, but just want to look at this for a second. We know that if it was a half a rotation like this, it would be 3.14. So I think it seems pretty reasonable that we found that this angle is 2.5 radians. Sometimes it feels weird for you to get an angle measurement that's so small, like 2.5, because when you're used to working for degrees, with degrees, your angles are typically a lot bigger numbers, but radians are so much bigger than angles, or so much bigger than degrees, that the same angle has a small number like 2.5. Okay, last one. We've got this insanely large truck. It has a tire with a radius of 5.3 feet. We want to know how far the truck will travel if its tire rotates 3/4 of a turn. So this is kind of interesting to think about. You've got this point on your tire that's touching the ground, and as your tire rolls forward, essentially the distance you move forward is the arc length of your tire. And it's hard to picture that, but I think one of the best ways to picture it is to take a piece of tape or a roll of tape and hold the end of the tape down and unroll the tape, and you can see that arc length rolling off there. So we've got our tire turning 3/4 of a turn, 3/4 of a rotation. Well, in radians, 3/4 of a rotation is the angle 3 pi over 2. So that's our angle. In radians, the arc length formula tells me that the arc length is equal to r times theta. So we have a radius of 5.3, and we're going to multiply it by the angle 3 pi over 2. We're going to get a decimal, go ahead and get the decimal approximation here, times 3 pi over 2. So we find that this truck rolls forward about 25 feet, even if its tire is only making 3/4 of a revolution. These are huge tires, so they don't have to turn a whole lot to move that thing pretty far forward. Okay, so that's it. So we've got arc length, in degrees, arc length, and radians. So just pay attention to which type of angle measurement you have, and practice sketching out some radian measures, and we'll continue practicing that throughout our unit. So that's it.